Let's look at another example of applications of the derivative. So let's read this example, or you can pause it and read it. I'll read it to you though. An open box with a rectangular base is to be constructed from a rectangular piece of cardboard 16 inches wide and 21 inches long. By cutting a square from each corner, then bending up the resulting sides. Find the size of the corner square that will produce a box having the largest possible volume. Disregard the thickness of the cardboard. Okay, so a number of things here I highlighted earlier when I'm reading it. Let's just do it again as I'm going through it. So read it once all the way through, then start reading it again. An open box. Okay, so nothing on top, right? Rectangular base to be constructed of a piece of cardboard, and then you have the 16 inches. Okay, so that's down here. So you would start drawing right now, basically the rectangle, and then 20 inches long, and then you cut squares from each corner. Okay, so it's a square each corner, and then bending up the resulting sides. Okay, then you want the largest possible volume. So you got to think in terms of what are you trying to maximize? What's the maximum amount what are you maximizing? Volume, area. I'm not sure what else you could do with the cardboard box, but so basically, we have the picture right here, of course, and let's just go ahead and start drawing. So even though they give you a picture, I would always draw your own picture. So I'm going to draw in my rectangle like this, and it'll automatically make it nice. Otherwise, I'd use of course, I didn't do it that time. Otherwise, I'd use straight edge and stuff. Not sure why it keeps not doing it. It's weird. I draw it really bad, and it does it, and draw it good, and it doesn't. All right, so here's my rectangle. And it's about 16 by 20. What is it, 16 by 21? So that's pretty close. I mean, it doesn't have to be perfect at all. But that's what I'm going to start with. So I got to start thinking in terms of what it's going to look like. So what I have is the long side is 21, like this. And then the short side is 16, like this. But then I'm going to bend up the corners, like here, each side, and fold it up. So I don't know how much that is, but it's going to have to be the same on either side. So that is what I'm going to call X. So we don't know what it is, but we're going to call it X. You could call it Y, you could call it A, you could call it whatever you want. Okay, so we don't know what that is. So that means the resulting side, once you bend it up, is going to be, and let's just look at this one now, is going to be the 21 minus 2x. So you have, of course, two of them, right? So you have 1, 2. So this distance right here is 21 minus 2x. So that's what you have to know. So 21 minus 2x is this side right here. Okay, well, it doesn't like to do that today. And then this side right here will be the 16 minus 2x. 16 minus 2x. Like that. So when you're looking at, that's a little better picture that they drew in advance. When you're looking at that, then that's your box that has that volume inside. So it has all this volume here. So now that we have the picture, so now we're kind of going down the list here. We read more than once. Started thinking about it. I sketched the diagram even though it was already sketched for me. I defined variables, basically by the picture is good enough. Write down facts and relationships. Well, that's where you need to know, well, what's the volume of a box? So, well, let me back up. What sort of, I already gave you the punchline there, but write down facts and relationships. Well, are you talking about area, volume? What are you talking about? We're talking about volume in this case. So volume of a because that's what it's saying down here, largest possible volume. So volume is always length times width times height of a rectangular solid. So that's the relationship that's given. Now you have to write the length times width times height in terms of your dimensions below. Okay, so we have everything but really the height there, which we talked about. The height, once you bend it up, will be x. So what's your formula going to be? So take a guess at what your formula is. And you basically want volume in terms of x. Okay, well, volume in terms of x will be, I'll say length is the 21 minus 2x. Width would be the 16 minus 2x. And your height will then just be x. It's length times width times height. All right, so that's the function you get. And so now, now maximize that. So now maximize volume. And that's not really the word to use. Really what you're doing then is you're trying to find max and mins of that function on its domain. But I like to call it just maximize. You're trying to find the maximum value. So let's, next I said domain, let's consider domain of that function. So domain in terms of x. Well, you got to look at the picture. You got to think about the picture here and what that says. So like when you cut it, how far can you cut it? Well, basically you have to look at the either 21 or 16 because that's the length and the width of the box or of the cardboard. So if you cut it, you can't cut it past here, it wouldn't make sense. So really it has to be between 0 and 8. So it has to be this cut right here for your x is in that interval. Can't be 0, you won't have anything. Can't be past 8 or you wouldn't have the right it wouldn't make sense to go over here. Just doesn't make sense, right? You got to go 0 to 8. So if that doesn't ring well to you, think about why it has to be 0 to 8. So domain of x is in that interval. So domain is 0 to 8, or so that's it. So this is probably the notation you see in the book, but this notation is heading towards higher levels, basically. So that's the domain of your value. So you can test endpoints, but it really wouldn't make sense. So you have to find a maximum value within that. Okay, so now what do you think you want to do next? Well, you have your volume function and it's in this form. So we need to multiply this out and then do your v prime and v double prime. Okay, so we get v of x, multiply that out, and it looks like I did it but didn't show the work. So let's just multiply it out together. I'll give you, so try that, and then you can see you get this. You factor out a 2 in the whole thing, and I get 160. So verify this: 168x minus 37x squared plus 2x cubed. All right, so then, so I do the dots in between because I didn't bother showing that work in my notes. So you can do all that, multiply that out. You'll see you have you'll end up with a 2 in common once you add everything together. So that 2 won't matter once you go through the derivative and stuff. So v prime of x would be your next step. Take its derivative, and you get the 2 just stays there. And you get 168 and then that's just 1, and then minus 2 times 37 is 74, x, and then plus 6x squared. All right, so then you're setting that equal to 0 and solving. So you might as well get your critical values, and they're going to be nice values because it's a polynomial. So you get factor out a 2 again, so you have 4, and then when you factor again, check this, you get 3x minus 28. So pause and do this factoring on your own. I really don't care how you get it. You could use quadratic formula. It doesn't really matter, but you should be able to factor pretty quickly on that. So that's equivalent to x equal to 28 thirds, or x is equal to 3. So what is 28 thirds? So is 3 in the domain? So which one is in the domain? So the next question is basically that. I'll say that again. Consider domain. We want to consider domain of the function and see which one is in it, if either or neither. So 28 thirds reduces to what? Or if you, so that's 9.3, is it's 27, so 27 and 1/3. So 28 thirds, we can see 28 thirds is not in 0 to 8. So we throw it out. We don't consider that. We only want to then consider x equal to 3. So we want to test x equal to 3 in v double prime of x. It's the only critical value in the domain. All right, so you have v prime, so you take v double prime of x equal to, and you get 2 times negative 74 plus 12x, and then you're using the second derivative test because v prime is equal to 0, so excuse me, v double prime of 3 is what you're testing. You put in v double prime of 3, you get negative 74 plus 36, less than 0, so that implies a local maximum. So we were trying to maximize the volume, so that is a maximum value. Okay, so in this case, testing endpoints would not make sense. It may sometimes, but in this case it doesn't, would not make sense. All right, so then does cutting 3 inches on either side make sense? And it does. That seems very reasonable, that cutting 3 inches here and 3 inches here on either side, bending it up appropriately would create your box, and that seems a reasonable answer. So that's what you say. So you say cut a 3 by 3 inch piece from each corner. That's all you'd have to say, but I'm going to write it out to maximize volume. All right, so then you can go on to say, did it ask for dimensions? What did it actually ask for? Find the size of the corner square that will produce a box having the largest possible volume. Disregard. Okay, so that answers the question. It could have asked, what are the dimensions of the box? So this is a bonus answer for you. The dimensions of the box are, and then you're just going to put it into the sides. It ends up being 15 by 10 by 3 inches. All right, that's the easy part, actually. Okay, let's go on and do another one. I'll go ahead and grab it from over here. It's right here. Copy. Next question is this. Just don't leave it big like that this time. That's okay. All right. So a circular cylindrical metal container, open at the top, is to have a capacity of 24 pi cubic inches. The cost of the material used for the bottom of the container is 15 cents per inch is cubed, and that of the material used for the curved part is 5 cents per inch is cubed. Okay, so it's a different. So basically the bottom costs more. Maybe it's more difficult to make the bottom of the container. It's a cylindrical metal cylinder, so it's going to look, like a Coke can, like that. Okay, but the bottom is more tough to make for some reason. Maybe it's thicker. Who knows? And that the material used for the curve. Okay, if there is no waste of material. Okay, so fine. Find the dimensions that will minimize the cost of the material. So basically, you don't want like a really big base and short sides, right? Because that's just not going to work. You have to have sides and a base, right? So you're going to have to figure out what that's going to be. Now, it's open at the top, so there's nothing on the top, but at the bottom you have material. So it's not really like a can that's like this, but maybe that's all you're looking for. So what's the first thing you're going to start doing? We read it a couple times. You could write down. So let's do it like in a different order maybe. So read more than once. We did that. Sketch diagram, label. So maybe you start writing down known facts and relationships. You could do that first, because what are we talking about? We're talking about a cylindrical cylinder. So maybe you look up in your book and you find out that volume is equal to pi r squared for a cylinder. Is that what we're looking for, though? Is that what we're trying to find? So pi r squared h, sorry. Volume is pi r squared times h. Okay, well, let's see, what else do we know? Because that's the actual volume. We also know that what else? We know surface area. So the surface area, we'll call that S. So surface area is basically the base. See, I got to start drawing a picture. It's just the base times the sides, right? So it would be pi r squared plus the sides, but it's not. It isn't 2 pi. It's just 1 pi r squared. So it's the area of the base, and then the area of the sides. The sides then are the circumference of the circle, which is the circumference is 2 pi, and then times the height. So 2 pi r and times h. So you got to make sure that these dimensions are correct. You have r squared and r times h. So that's the surface area of the figure given. So you got to be careful what it is. I personally would have drawn pictures first. I don't like just drawing those. So what I'd come in here and do is, okay, let's talk about our our cylinder. So I would say, let's see what we want to use when we draw our cylinders. We have our cylinder. For some reason, this isn't working as well as it used to. I'm going to just keep trying it until it works, because why not? I mean, so you can stretch this out like this, make it a little smaller. Go over here. So I suggest drawing as big a picture as it makes sense for your work. Like that. And then we're going to copy that and paste it again. And then it tells you when it lines it up on here, which is nice. So I'm going to guess it might look something like that. Okay, so then you have your sides. For some reason, that's just not working like it used to either. I need an update. Need to fix that. All right, so there's your sides. You have the height of this thing, right? We don't know what that is. Okay, then you have a radius. R, we don't know what that is yet. We'll start figuring it out in a bit here. Okay, this part is open, so nothing here. It's empty. You have a base down here, so this is all here. There's your base. That's a different cost than the sides. Then you have your sides, which are all of this. Okay. That actually goes all the way down to like that. So something like that. Often what you'll do is you'll do dotted in the back. I'm not going to like redraw it, I'll just erase it. So this back here is like dotted. Doesn't look very good now, but whatever. All right, so then so surface, so let me put this in a little note here. We only oops, I can't spell apparently. Only one end. Otherwise you'd have two, right? So you have, normally you say area of the base and area of the top times 2, and then you do the sides. The sides for surface area is the circumference around the circle times the height. That's always your 2 pi r h. So this, normally you have a 2 there, but we don't because the top is open. All right, so now what we want to do, so are we going to use volume? What did it ask for? It asked for what? If there is no way to find the dimensions that will minimize the cost of material. So cost of material is having to do with what's given. There's nothing really to do with volume, right? So we don't really need volume. That's not really in our calculation. So we want to develop now a cost function. So figure out, so that's really your next big jump, is figure out a cost function. So the cost is going to be basically just 15 times the sides plus 5 times, or no, what was it again? Oh, it does, so a cylindrical metal can open at the top having a capacity. So this is given as a capacity. Oh, that's where it's going to be used, huh? So that's volume. Capacity is volume. So you have inches cubed. That means it's volume. All right, so you're looking at 15 cents at the bottom and 5 cents on the sides. So this is the sides, which corresponds to the 5 cents. And this is the base, which corresponds to the 15 cents. So it's 15 times this guy, and then it's 5 times this guy. So cost function is that. So it's 15 times pi r squared plus 5 times 2 pi r h. All right, so then what I have is I also have given that the volume is 24 pi is equal to pi r squared h. Okay, so this is given. I want to just try to be somewhat clear that this part is given. It's right there. So here we have a cost function, but the problem here is we have r and h. But we have this relationship, so this is the relationship of the sides, okay, so, or variables. This is the relationship of variables. Right, that was one of our things to look for. Determine, write down known facts and relationships. So eventually we got to that relationship between the sides and base. Okay. So knowing that, we can then solve for, and then this is where you gotta have to just know what's probably best. What's probably best is to solve for h. So you can find it in terms of r. So you have h equal to 24 over r squared. All right, so then now we have your cost function just in terms of r. So your cost function is going to be 15 pi r squared plus 10 pi, and then it's r times 24 over r squared, substituting in there. Okay, so we substitute in and solve, so we get 15 pi r squared plus 240 pi over r. We can simplify a little further, do a little work on it, and you get 5 pi times 3r squared plus 48 over r. So that's just factoring out a couple things. All right, so now that's our function we're going to be using. So we're going to be using, this is our function. We want to minimize cost, so find the minimum. Okay, so if it wasn't up there, read that again, and you're trying to find the minimum cost. All right, so C prime, so take the derivative now, C prime is 5 pi, and then you get 6r minus 48 r squared equal to, and then you just simplify, 30 pi. Put it with one denominator, so it's r cubed minus 8 over r squared. Set that equal to 0 and solve. The numerator, just to point this out, this actually factors to a difference of cubes, but the second quadratic is not factorable with real numbers. So you just get 2 and 0. So let's talk about, again, domain. So your R for domain, really, it could, I mean, there's no, it can't be 0, right? And then is there any sort of restriction on the radius. I mean, basically, as the r goes out, h would have to go down infinitely. So there's really no restriction on r other than positive, right? So r has to be positive. Obviously, it can't go on forever, so it's got to stop somewhere, and then you have maybe just a tiny little height, but it is going to be there. Okay, and obviously it's not. It needs to make sense too. You shouldn't get something really strange. All right, so then our critical value. So now when you set this equal to 0, you have r cubed minus 8 equal to 0, and that implies r is equal to 2. You also get just this. I have to show you this. You get r minus 2, and then you get r squared plus 2r plus 4. And so that's complex solutions. Okay, so r equals 2 is only CV in domain. There's only critical value in the domain. What is your other critical value, though? I mean, just if you were just looking at this function here, what are your critical values? You don't use complex, so you would eliminate, you ignore that, but you get 2 and also 0, right? You also get r is equal to 0. So you could say here r equal to 2 and 0, and then you omit r equal to 0. Because you can't have a 0 radius. All right. So then next thing, let's do C double prime of R. C double prime, you get, where'd that go? Right here. Okay, so when you do this, so you can do the second derivative. There's ways to argue this without doing the second derivative, but we can. So we'll go ahead and do it. So the 30 pi stays out there. Denominator is going to be squared. So let's go ahead and do it. So you get 30 pi. And you only have to go far enough till you know that it's positive or negative. So it's a local minimum. But anyway, you get 30 pi, so derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So simplify that numerator. 30 pi. Denominator will always be positive because it's to the 8th power. 3r to the 4th is always positive. And it's minus 2r to the 4th. Try this again. So 2r to the 4th, and I'm going to say minus 16r. And then it's 30 pi. 3r to the 4th minus 2r to the 4th plus 16r over r to the 8th. Double check my work here. I don't have this one written down. So derivative of the top is 3r squared times the bottom minus the top times the derivative of the bottom all over the bottom squared. Oops. That's not going to change my result again, but Bottom square gives you a 4. So denominator is always positive. All right, so that's, then multiply. Let's check my multiplication. So distribute the 2r, so you get r3, 2r to the 4th. 2 times 8 is 16, minus 8, distribute, makes it a plus. Okay, so now let's do c double prime of 2. So all you're really looking at is 3, 2 to the 4th, minus 2. Oh, I could have simplified that. All right, I can't leave that like that. All right, yeah, let's simplify that. So you're coming back here, we get 30 pi. And so those are the same powers, so that's just r to the 4th plus 16r. Okay, that's easier to analyze because if you put in a positive value, you'll get a positive value. Okay, so that, therefore, now it's easy to check. C double prime of 2 is positive, right? Everything's positive, but if you put in a positive here, this will remain positive, and then you're adding positives. So greater than 0, that implies greater than 0 is concave up, right? So that implies a local minimum. All right, so then so the radius should be 2 inches. And it makes sense. So therefore, the radius should be 2 inches. So what you end up getting is a radius of 2 and a height of 6. So this is 2 and then this is 6. You can check that. And again, that's open at the top. Okay. Next one entails, again, let's see, either similar triangles or Pythagorean theorem. Figure out with a cone. That's always a fun one.